few details about him. And also, I want to thank Subodh for bringing this conduct here. Actually, we are indeed talking about a kilometer scale model. So we want to learn more from you today, what you are doing and how the things are. So I just want to say a few things about him. Dr. Dipankar is a senior scientist at the Institute of Atmospheric and Climate Science at ETH Zurich and scientific director of Exclaim project. He may be talking about that project today. We will hear from him. And his research focuses on scientific computing and turbulence, with a particular emphasis on advancing high-resolution climate and weather modeling capabilities. Prior to joining ETH, Dr. Dipankar led weather modeling and prediction branch at the Center for Climate Research, Singapore, where he played a key role in developing national numerical weather prediction and climate modeling systems. He also contributed to development of eddy resolving capabilities for icon modeling system during his tenure at Max Planck Institute for Meteorology in Hamburg. Dr. Dipankar did BTech from IIT Kanpur in aerospace engineering and PhD in turbulence from the University of Pierre and Marie Curie, Paris. His work continues to push the boundaries of computational climate science, particularly in the context of high-resolution simulations. So actually, it's a very dear topic. So I hope you all will enjoy. And if there is still time, call your other friends who could not be sitting here right now. Tell them that this is a very forefront topic. Everyone should listen to it. Thank you. Welcome to the Institute, and please continue.
Thanks for the nice introduction. Do you hear me well? Yeah. Okay. So this works. And thanks for the nice introduction and for having me here. And I also appreciate Subodh and his team. We have been having some conversation over. Okay. We have been having some conversation over past months, and for me, it's a great pleasure to be here and talk about the work we have been doing over last 4 or 5 years. But it's been a journey for me personally. I think I have been trying to. In my personal career, I have been trying to push the grid resolution for last 10 years, and in this journey, I have been to Max Planck, where I worked with Bjorn Stevens. Now he's also in the forefront of pushing this limit. And then I had an occasion to be with one of the previous directors from ECMWF, Alan Schellen. And he also had been quite provocative about kilometers, and point being, going to a regime where you start to resolve processes that you otherwise cannot. Here, I mean, over 10 years, it has been a long journey. I'm still thinking where to stand, you know. This is high.
Yeah, right.
I think this is better. Yeah. It's been a long journey for me. And at the same time, I realized after coming to Switzerland that it's been a long journey also for people who are not from science, people who are more close to machine, for example. It's been a long journey. Since 2010, for example, people have been trying to get to a regime where you can start to simulate at 1 kilometer, let's say, globally. So this story more or less captures everybody. So I represent almost, okay, let me go to the next slide. Yes, it changed here. Thank you. So I'm giving a talk that encompasses efforts from people involved in the Center for Climate System Modeling. It's a It used to be a competence center, and now it is going to become what we call a technological platform. So it encompasses mostly, not mostly, all of them are Swiss research institutes, ETH, WSL, MedService. MedService is Meteo Swiss. And now I started from being at Exclaim, which was a short-term project with predefined goal. And now I will take over some of the responsibilities in model development as CTOSM grows. We, of course, have partnership across Europe. So CSCS is the National Supercomputing Center in Switzerland. DWD is the German Weather Service, and Max Planck Institute in Hamburg. And again, as I said, this is a story of collaboration that has happened over the years. I am only here. I'm involved in this journey with them for last 4 or 5 years. Okay, I'll start with the motivation. Why we started, or people have been trying to push limits in terms of grid spacing. Then I'll go for describing this complexity as you go to kilometer scale globally, you hit a limit for science as well as for technology, for computers, and that invokes collaboration with people from different background, different expertise. Then I'll briefly go through the efforts that we have had, we are working on, and we plan to do in the near future. And the future, by future I mean the next 2 to 5 years, we are trying to work towards a climate and weather platform, which I will talk about what it is. And this is interesting that we started with a plan to develop a model. And on the way, we realized that this is not enough. You really have to collaborate with people of different expertise, scientists from different regions of the world. And that's when the idea of this platform came about. And that's how it is now in the future. Okay. And the last point, feel free to interrupt. So, I would prefer if you have an interactive session over here. Okay, it works. So as I said, it's a journey of reducing model bias. It's been happening for over the years. Roughly, let's say our modeling systems have 2 sources of errors, So the first one is dynamics, is the left-hand side that we resolve on the grid scale. And there is physics, where we start to represent processes. Cloud microphysics, for example, turbulence, for example, how the sun interacts with atmosphere, radiation. Gravity wave, how gravity wave, which you don't see essentially, but how it interacts with atmosphere. So these are the processes that you try to represent somehow empirically in your modeling system. So these 2 representations have their own sources of error, and these 2 errors behave differently. Dynamics is well behaved. You discretize the system. You have a numerical scheme that works on those discrete space, and they have errors that we know how it behaves. It decreases as you increase the number of grid points. Error decreases, and that we know, that we understand. Now, the world of physics is a bit complex. It's like a dream for many people. People imagine how convection works, and you try to represent it on a modeling system. It's really people's mindset. It represents people's mindset many times. So people come up with, this is apart from ICON, different tuning parameters. I think every modeling system has a set of tuning parameters that you tune, and then you adjust your results. So physics, as you increase resolution or you change resolution, you adapt your tuning parameters. And they have been doing a great job over the past years. We have quite reliable numerical forecast, numerical projection of climate. It has done a good job. But underlying assumption in this parameterization is that the large scale, they drive how the small scale should behave. Or essentially, small scales don't feed back to the larger scale, then the flow of information is mostly one directional, which is fine on the mean scale, but not otherwise. This is where I'm going to talk about scales now. You see, so this picture, so this is a nice picture from Heinz Fortart from 1962. It's in German, sorry about that, but I think most of the words are similar. This is cyclone scale, this is filter system, this is we start to talk about deep convection, cumulus convection, turbulence, scales, sound waves, gravity waves. X-axis is space, time axis is y, and he is trying to characterize different phenomena that we observe where they belong in space and time curve. So the reason I am putting this is what I found that in 1960, he was able to see that you have pockets of scales. They have different scale. Planetary scale works on very large scale, as opposed to convective system, which works on kilometer scale, but they are tied. They are somehow interconnected. I don't know whether he did it intentionally, but he has a wrapper around it. They are interconnected somehow. For some reason, he has a scale separation here, which I don't understand, but we don't have to go there. This means that this is a canonical kinetic energy spectra of atmosphere. Basically says the same information, that the information from very large scale to very small scale is not in one dimension. It works two-way, And this is an interaction where is no scale separation. I mean, the two know about each other. But when we parameterize, we of course have to simplify. So when we simplify, say you truncate, you have a grid space. We say that this part of information is what is captured by the grid scale, and this part of information mostly acts as energy sink. It sinks the energy, and in the mean sense, the energy flows in one direction from large scale to the small scale. And where we cut, where we provide this filter, depends on the grid scale. For 100 kilometer grid spacing, you start to think that convection is more or less energy sink. When you go to 100 meters, start to think about LES, you start to think that 3D turbulence is energy sink, which makes sense. Point being, again, as I said, this thinking inherently assumes that the large scale governs how small scale should behave, which is not always true, at least not when you think about fine scale information. Now, what happens when it is not? So this is a result from one of the simulations we did. So I'm plotting mean EKE, eddy kinetic energy. Eddy kinetic energy spectra at 500 hectopascal from two simulations, one at 20 kilometer, which represents state of the art, and one at 2.5 kilometers globally, where you start to resolve, let's say, a storm. They have all been remapped to 50 kilometer grid spacing. And what I personally found interesting in this picture was, okay, so the blue line is 20 and then the red is 2.5 kilometer. Is that, of course, we have finer resolution, so you start to inject energy. You have more energy being generated at smaller scale, which is fine, which I expected. What I did not expect was this picture, that this energy is very nicely being transported upstream to the larger scale, and you start to see some change in large scale, very large scale. And mind you that this is averaged over 1 year, over 3 ensemble members, at the same time zonally average. So it's quite robust picture. In the very mean sense, you start to see that energy which is injected at a small scale feeds back to the very large scale at planetary scale. And then, of course, it has to feed back to the small scale. I think Bjorn Stevens called this, weather affecting climate. Whereas in the previous generations, we had this thinking of climate driving the weather. Anyways, so in the simulation, what really happened was this x-axis is latitude, zonally average picture of zonal mean wind. Pressure is y-axis, 20 kilometer, 2.5 kilometer. It's hard to see. One will have to take a diff plot, but it was just nice for me to use it here like this. And you just follow the arrow and trust me that the Hadley cell actually moved a little bit, but it moved at higher because of increased grid spacing, reduced grid spacing. And the jet, it became stronger at higher resolution. Again, point being, smaller scale do affect larger scale, and the energy has to go back to the small scale at the same time.
I have.
Yes, please. Yes.
Whether it is due to the clouds and convection, or it means where exactly you have seen this kind of higher energy in the small scale?
We haven't quantified that much now.
You go to the previous one. So when you are saying the arrow from the upper side, the other side. So what you want to show here, this side is it is saying that how the energy dissipating at the small scale, and that's why when you go 2.5 kilometer, you have the higher energy because you are resolving the smallest scale things there, a small scale. But what is this coupling going other side? How it is giving feedback from small to the large scale?
So now I will go up. So this is where we have ITCZ, strong rain band system. Then the wind comes down, and this makes the Hadley cell. So again, the small scale, now here small is 2.5 kilometer. At kilometer scale, you change the behavior of convective system, how it behaves. It was much stronger here, thereby the draft, the wind that went into this direction, poleward, was much stronger, which made this Hadley cell go wider a little bit. So this thinking of small scale sinks energy, dissipates, is not always true. I mean, in the mean sense, it does.
It is relative. How small, that is relative.
Yes.
It all depends what you said. No, for how many kilometer or maybe meter, it's all.
Yeah. Okay. Now, again, the same modeling system, 2.5 kilometer, and this is a result from an uncoupled simulation. So the previous simulation was aquaplanet, there was no land. This is uncoupled, you have land but no ocean. And here this is a figure from Andreas Prime. He has interest in mesocell convective system and extreme, weather extremes. So he is looking into 10-meter wind near the surface, PDFs, global compared to HAD ISD observation data. They have a good network worldwide. Specific region, West Central Europe, Northern Australia. I mean, somewhere it does well, somewhere it doesn't. But the point being, overall, at this scale, you start to capture 10-meter wind, which is really very hard to capture. Extreme events, yes, it's much of tuning involved probably. We probably have to push resolution even more, don't know, but it does fairly good job. And mind you that the model hasn't been tuned yet. Tuning is another challenge at this resolution, but this hasn't been tuned yet. Okay. So far it was all about why we even think about kilometer scale. Point being, small scale feeds back to the larger scale, and the information also goes down. So the entire thing has to evolve at this spacing. But to get there is a challenging task. It's a challenging task, but one has to take up because weather extremes are now reality. We see them happening more often. Now, it's a challenging task for science because it's a new regime for most of us. It's not easy to tune. I mean, when it was coarser resolution, you run the model 10 times, you can tune it. Now you cannot run it 10 times so easily. So it's a But still, it's a regime that we can still play with. We understand. Technology is something new for us. And here it pushes technology at every level, from chips to file system to disk space. Everything is at the cutting edge when you are simulating at this scale. So this is a challenging task, I must admit. Now, the part that we focused more over the past few years, and this is where expertise lies in ETH, is how to compute fast but consume less energy. So this is a picture from one of the papers recently published from DKRZ, Germany. So this y-axis is energy per simulated day. So how much energy you consume when you simulate for a day in this of the simulated day. This is the speed, time per simulated day. So as this decreases, you get faster. As this decreases, you become more efficient. The figure shows that when you go faster, you tend to consume more energy, which is true. And these energies are quite a lot. So the aim has been for last 10 years in the community to come to this regime where you are fast, but you're consuming less at the same time. And this is what we have been trying for last 3 years. Now, machines have evolved over the years, and the literature suggests that these machines are more energy efficient. So this is what vendors says, and I must admit that we haven't been able to make precise measurements yet, but we believe them for now. But there's a condition that to be able to use these complex machines. So these are machines, for example, from previous generation CPU-based systems, you're moving to a host where host is CPU and a device where device is GPU, and the two has to interact. It's more complex, it's a heterogeneous system, but you have to be able to use this system efficiently, properly, let's say, to save energy. Now, this is a nice picture from Thorsten Hoffler from ETH. He is showing how much it costs in terms of energy to move data on a chip. And compare it with this. So this is typical cost of a single floating point operation in picojoules. Doesn't matter, 100 picojoule. Point being, I'm not sure how many of you are aware that when we run these large simulations, we have to do this domain decomposition. So our domain is divided into different parts, and each compute nodes handle one part, the other one handles other part, and then they talk to each other. This is the cost of moving data between neighboring nodes, not far away nodes, from neighboring nodes, which is about 25 times more than cost of a single floating point operation. It's expensive. It costs a lot of energy. At the same time, it is of course challenging, and the community in the last 15 years, to my understanding, the computer science domain has been trying to find an efficient way to work this out. But overall, it's a challenging process. And the takeaway is, at least in my mind, is that you don't move the data at all. You just compute where the data lives. But when you try to do that, your code becomes something like this. So most of you are aware of Fortran. I took a bad example. I wanted to show something bad. Mostly it's not that bad. So this is the part of changes in the code that you have to do to make the thing go efficient on a GPU machine, on a heterogeneous machine. The readability of code decreases. You cannot understand what is this code doing anymore.
This is basically you are putting the OpenSSC Pragma inside the Fortran.
Inside the model.
Fortran program, no?
Yes. Yes. This is typical approach. On top of that, it is error prone. There are now several literature that suggest that these approaches are error prone. Simply put, one needs an expertise. I mean, to me, it was new. It still is new. One needs an expertise beyond your domain, and that's where you start to collaborate with people you know more about those things. So this is a nice picture, at least to my mind, how the model development landscape has evolved over the years. I mean, in 2010 or before 2010, it was me who used to write program and run the thing on computers. In 2010, I think we had this concept of scientific programmers. So I would write something, hand it over to scientific programmer. He would parallelize, make it efficient, and run it on the machine. At the same time, machine is becoming complex. Now we have me. I'm much farther away from compute. Scientific programmer is there, and we have, let's say, computer scientists who know much more about these architecture and the compilers and how they interact with each other, and you have to work together with them. And this is it. I think this is why it has become a journey for me personally. That over the past few years, you start to understand people and how you talk in the same language yet try to achieve something similar. But we did. Um, we now have a system that runs, does the job, but we wanted to do more than that. I will tell you the reason later. So we started with a vision that this is how a typical model looks like. Let me see the time. A typical Fortran model looks like this. You have a name list file, you modify the name list file, then there is a driver that drives different components in the model. Different components being dynamical code, different physics, different terminal scheme, ocean, and everything is inside the same binary. You compile the whole thing and you run it. Which to many people is makes the job of making this code work on new machine very hard. So we had a vision of breaking down this code into different pieces, those pieces that we can test. So we call them granule because they are smaller granules of this larger component. And CI means continuous integration, which means these granules are continuously being tested, which is new for our community. I mean, we are used to testing the whole thing. You run and you compare with the atmosphere that you understand. So this is the vision where we would like to go. You have testing for each component. You have model infrastructure. You have a driver. Everything is written in something like Python. Why Python? Simply because Python is easy to use. Most of the youngsters, they don't know Fortran. I like Fortran, but they don't like Fortran anymore. Python is there, it's easy to use, and it exposes you to the large world of Python. You can do many things once you are in there. So Python.
Are we getting the accuracy of Fortran?
Yeah. So you have to believe on the CI, on the testing that you put, and it tests, it works. Now, I think it is important for me to take some time and explain, tell you briefly about this tool that we use called GT4Pi. So it's a DSL, domain specific language. So it helps me write code. And I will write very nice looking code, and GT4Pi will do rest of the heavy lifting. It will generate me binaries that will then run on the system. So it separates concern. I'm a user. I don't know what OpenACC is. I don't need to know what MPI decomposition is. I just write plain and simple Python code and you run it. It should run. So what happens is that the large code, which in icon look like this, and I'm sure it will be same in any other model. This is an operator that does second order diffusion, numerical dissipation in the model. And the code becomes these many lines. Frankly, I still prefer Fortran, but this is much simpler. This is much simpler, easy to understand, and you don't have to worry about OpenACC pragma, OpenMP pragma. These all disappear, and this DSL takes care of all those complexities for me. So ETH had a long history in working towards this DSL. I think for since 2008 or 7, they have been working on this. And now it is at a stage where you can use it in an Earth modeling system, quite mature.
The speed up is same, like at the same time.
You'll see something. So where we are right now, we have to get everything green. We are not there yet. We're in the middle, but we still have some more time. I think by next year or so, we should be there. What else? Nothing. In terms of while you develop software, at the same time you run simulations, you make sure that the software is doing what it is supposed to do. It's a showcase movie. How do I run the movie? Yeah. So it's from a 2.5 kilometer simulation, and he's plotting, I think, near surface vorticity. And I think we wanted to see some of the cyclones. And at some point, he will zoom out to the whole globe. Where is it? Let me zoom out. See. The fidelity of information is amazing at this scale. See that cyclone moving out. Here, the point was to demonstrate that the capability is there. Not only us, and there are a few other groups who have similar capabilities. And for me, it was just impressive to see such fidelity in simulation. And the information is quite detailed. Are you still able to hear me? Okay. He will go to Manila. It has to.
Participating.
I think he also compared for one of the cyclones that hit in 2018 in the US.
This is atmospheric only, right?
This is so far, yeah. Bad example.
Very good.
We have to do the same animation with once ocean is coupled. Yeah. Yes.
Very good.
I'll move forward. So this is kilometer scale, and now I will switch to the next animation. And this is where I wanted to briefly mention about the usefulness of Python word. So this is, of course, street level. So this is towards urban modeling, that capability that we have been working on. This is an idealized simulation of few building blocks, and the vertical section shows wind magnitude, and the horizontal section shows horizontal vorticity, and those lines are streamlines. He has only shown it for between two blocks, not rest of the domains. So this is an interesting story because Jacobo, he's a postdoc, and he had a choice to use Fortran, implement these new technique, either in Fortran icon or in Python icon. He chose Python icon. And the whole thing was ready in a few days. And not only that, you make a mistake, you don't have to recompile. You just run like a Python code. You put a break statement. You can plot at that line, see what is going on wrong. It increases your productivity significantly. Yes.
Those are the streamlines.
These are streamlines. Yeah. Okay. Performance. Maybe you asked about performance. So this is default implementation. There hasn't been any performance tuning so far. And here, focus on the blue line, for example. This is total performance gain. roughly 10 times faster. So
Noted one
the
is
solid is OpenACC. OpenACC is about 3 to 5 times faster than on CPU. And this is OpenACC. The dashed line is DSL implementation, GT4Pi implementation, which is about 10 times faster if you are in this region. As you scale, you start to lose because the data transfer start to dominate. And this is without much performance tuning. Now there's a new kid in the block called performance engineer. So now you are at a stage where you are as fast as the default standard implementation called OpenACC to run something on heterogeneous machine. Now you want to go faster, for example, 40% faster. That's when you call performance engineer. He will strip down the code, not the code that you see, the code that is then run on the machine, and make it magic, not magic, but he will tune the performance to get to 40, 50%. We don't know how far we'll go, but yes, that's the goal.
this machine, how many GPUs in one node?
This has 4.
4.
Yeah.
Then it is going more complicated. So node to node communication is becoming increasing when you are going to 50 GPUs.
Yeah. Now, I mean, performance is good. This is one of the measures that we follow, and we try to be consume less energy. But what matters in real world for us, people like us who are from domain side, who want to look at the results, is that how fast it is running in the sense simulation day per day. So for example, if I want to run 10 years, and if my model can produce 1 simulation year per day, so in 10 days, I can finish 10 years, which is good enough. So we are aiming for something like 365 simulation day per day. So 1 simulation year per day. Right now, we get about 200 plus. It has to push more, work in progress. Yes. So I mentioned about performance tuning and performance engineer. They also need a tool to be able to tune. This is where this tool called DAZE comes into play. This allows you, the performance engineer, to see what is happening in terms of data movement, and then you can rearrange your data movement, let's say. So this is our first goal in the coming months, to be able to utilize DAZE properly to get to this 30 to 40 times, 40% faster. The same system will become operational at Meteo Swiss, the Met service of Switzerland, for their NWP forecast. And this system will then become, let's say, more operational. I will tell you why I call operational here at C2SM for kilometer scale coupled simulation. Okay. So much about the work we did, which was mostly about developing a model and being able to run. It took us 3 to 4 years. But then you realize, let me go to the next slide, that you do everything and you see in the results what you were expecting, what you were hoping for, and the results look nice. But then how do you analyze this petabyte of data? How do you tune your model? This is what I meant by new regime for a scientist, for a domain expert. Moreover, how do you disseminate this information to someone downstream? For example, someone here who wants to look into this simulation data to study something. This is not trivial. And we always had this in mind, but we never started working on it. So this is where we are at. And this is where we, okay, no, before that, I wanted to brief you through the data part. That our first simulation was Aquaplanet, so there was no land. There was about 1 petabyte of data, and there was single user, Mona. She was looking into Jetstream. And those were the first pictures I showed about Jetstream becoming stronger. Second user, prescribed SST. Data was about 5-6 petabyte, and there were 3 users. So one main user, and then few more people showed interest, and they started to look into atmosphere from different angle. Mesoscale convection, heat waves, monsoon. Third complexity, now we increase complexity, you attach ocean. We expect about 10 petabyte of data. So far, there are 2 users, 2 people interested to look into the data. But then this is not enough. The amount of data that you have, you need many more users to understand what is really happening and to really benefit from the depth of information in there. So this is where we are now working toward. Let me put the next slide. We have this capability so far to run the simulation on the machine it runs. The second capability where you bring users closer to the data is something that we are trying to work on. And I think we, as in people all around the world, probably needs to work together in this aspect. It's single Earth, one model, not one model, but one Earth. People from different regions, they know the local weather phenomena much more than people sitting in Switzerland, for example. So you need collaboration to evaluate a modeling system. We call this climate and weather platform. Some people call it digital twin. Point being the same, that you do something very expensive and you bring user to the data and you evaluate and make use of the data. As I said, this collaboration goes beyond Switzerland. So there are similar efforts by Destination Earth. It's a large European project. They are trying to make digital twins of Earth. Warm World, a large German project. We share technology. Technology being model components, GPU related technologies. And we'll probably also share file system related technologies. And there are efforts in the US with the DOE, E3SM project. So there we share know-how experiences in simulating at this scale, and similarly with Japanese group in Jamstack. I will stop here and provide a summary.
You said about that user for data. So are you keeping the data open for everybody, no?
Everybody is.
Or may somebody want to approach you, then you can provide something like that.
I think this is the mode that we will currently keep.
मैं ही बहुत पूछ रहा हूँ.
I think
Because you want the user, so that means you are providing the data so that people can use. So you must have some mechanism because it's a petabyte data.
we don't have any mechanism yet.
Okay.
We're still working on a mechanism, starting with which user. So we started with local user who can simply SSH to the machine and use the data. But this is not going to work out. It cannot scale. When we think about hundreds of users, you have to have an interface. And we don't want to transfer data from there to here, for example, petabytes. We want users to use compute over there.
Oh, so cloud compute kind of things you want.
Access to the local HPC over there.
Global software.
We don't have a good solution yet.
Because petabyte data and how people will use, and even cloud might be challenging. Cloud computing.
No, we don't want to transfer data. I think that we know. I think for me, the most important point here was to mention that I have seen personally that the technical collaboration has evolved quite sophisticated, not sophisticated, but quite nicely over 10 years in the region of the world, what I see, Germany, Europe. But scientific collaboration is not as strong. And it is, I mean, if I'm simulating over there, I cannot see how Indian monsoon behaves. I mean, I don't have much expertise over there. It is not universal. So you have to collaborate at some level with experts from different parts of the world.
Yeah, Anurag, very great effort. Very nice talk. My question is that what is next actually? So after all those doing, how you plan to transform it into a forecast system or global forecast system which can be used, or maybe globally, or it is you are only planning for Europe or thing, or it will be like a global forecast system accessible to all.
Yeah, I mean that's a good point, and good that you mentioned this. This was the part that I forgot to mention. When I had this operationalization of current release at C2SM for kilometer scale global simulations. Here, operationalization means we are not there yet. Right now, there is a person who runs the simulation, and there's a person who uses the data to investigate something that is of interest. But we want to get into an operational mode, that is, we run this couple simulation, fix the configuration, let's say 2.5 kilometer. For next 5 years, let's say this will be the configuration that will be run operationally, not so much operationally, but operationally. And it will be a service that C2SM will provide for the users outside. So users will not be able to simulate, but they will be using the data. Unless there is a collaboration, you have a scientific collaboration, you want to run something new, then you design an experiment, of course, you can run. But for now, it will be like a fixed configuration, real time, you let it run.
Yeah, thank you. Next one is that the last you showed the 2.5 kilometer couple one. So that would be from curiosity, scientific curiosity. We would like to see how the couple interaction from the monsoon region takes place. For example, these LPAs or MCAs, and then how they feedback to season.
That is of very prime interest for us.
So this figure I like very much, the energy from small scales to large scale. Yeah, everybody thinks that it is large scale to small scale. So this is a very big.
The other side, I also never heard.
No, we had one paper, but it was a big debate, that how this small scale is defining the seasonal.
But he explained very well when he went up and then
energy perspective you have showed very nicely. So this is how many years simulation? You said 3 years.
No, 3 ensemble members, each 1 year.
1 year simulation.
Each 1 year.
Okay, so it's robust, quite robust.
Yeah.
Thank you very much.
Thank you.
Like globally or some region, globally or
Of course, regional as well, but global is because it helps us, is much more challenging technically, so that allows us to stay aligned with the compute, because hardware is moving very fast nowadays. If we have to stay with the evolving hardware, or we choose not to evolve with them, if we have to evolve with them, we also have to push our boundaries at the same time so that we keep on collaborating. So this has been our mode of operation for a long time.
yeah, you mentioned that you are switching over to Python gradually. So is it not a good idea to put these things in a community model development perspective so that things will evolve much faster?
Yeah, very good point you mentioned. I'm not sure if you're aware, so not many modeling systems. So there are 3, now there are more, but the core global models, like the one MPAS, GFDL has FVCube, Germans have Icon, French has one, Japanese, UK. Of these, only 2 I think are open source. One is MPAS, and the other is Icon. It only happened last year or so. Because of all the other, DWD they do NWP forecast, and they are quite happy with what they're doing, and they do a very good job. But at the same time, the other community is trying to rapidly change the code. So open source is a way to go, and that's when the German government decided to make it an open source.
We look at the development with the WRF. It's a very great example of how things can.
Yeah.
So we should invite questions from the back. So, yeah, there are.
Yeah. Thanks for the interesting lecture. So, what is the vertical resolution of this model with a horizontal grid spacing of 2.5 kilometers? And another question is, do we have are there any uh, do you have differences in vertical resolution? For example, some regions where you can bring down finer resolutions to the boundary layer, where some processes are very important, and in some regions where the free tropospheric processes are important. So, do you have a setup where you can change the resolution
Locally.
from the XY space so that you can
That's a hard one. No, no. So in Icon, and then my best guess is, or any, not best guess, I know, none of them can do it when you're running a global system. So you have to fix your vertical level and then you go with it. Then otherwise you do nesting. Then you do a nest and locally you can change your vertical level.
I think he is referring nesting only.
Uh-huh.
We want to suppose do nesting over Indian region and have a global other places.
Yeah. That is possible. That is
The vertical resolution of this model.
This one had 120 levels up to 70 kilometers. 120 levels up to 70 or 75 kilometers model top. So probably it starts with 20 meter near the surface. It increases gradually and goes up to, I am not sure, maybe 500 or up to 1 kilometer near the top.
Thanks.
2.5 kilometer, you also change the radial resolution, right?
Yes.
You come from, let's say, 52.
Not in these experiments. I think in these experiments, we kept the same to be able to see the effect of horizontal spacing. Yeah. I think.
20 kilometers and also 120.
More questions?
Hello, sir. I believe you said that your model captures extreme events properly. I believe that's what you said in the slide. So that's something that we are struggling with, right? In finer resolution, sometimes extremes get averaged out. So did your group do something differently to capture extreme weather events?
No, it doesn't capture well.
That's okay.
It doesn't capture.
Never mind, then I heard you wrong.
It does okay, sure, but I haven't worked much. So, okay, for me, again, I said it's a scientific collaboration. Where is that figure? Yes. I think one would have to ask Andreas Prime, but this is where extreme events live. And this is where the observation black line and red model are more different.
Anyone?
No, but this is a journey. So probably I have not worked on this. So maybe, so this is at 2.5 kilometer. Maybe at 5 or 10 kilometer, model would have done even poorer job. It's a journey. Gradually, one reaches the black line over here.
Hello, sir.
Hi.
So my question is, so you said that we are aiming for more energy efficient solutions. So my question is, in general, I have read that Fortran is faster than Python and more energy efficient. So you said that more of like today's researchers move towards Python because it is easy. But if you're aiming for energy efficiency, uh, why can't we focus our efforts on Fortran? I mean, should we focus our efforts on Fortran instead of Python?
I mean, your question has several dimensions, but I'll stick with one. Python is not necessarily slow. It depends how you use it. Python is your interface to something much more that lies beyond. And the beyond, if you use efficiently, if you know, you can make it run efficiently. Python is not necessarily slow, but I understand the interface part in Python is slow. That is true. But it gives you something else, right?
Yes.
It increases your productivity. It's a cost that you bear sometimes. Yeah.
Okay, sir.
There is also computing dimension in this because more Python developers are available.
Yeah.
There is a computing dimension because Python developers are available in every field.
Yeah.
So that will be an advantageous.
Yeah, but it's very hard to get students who know Fortran.
You have to teach.
They have to teach.
All the students, we have to teach Fortran here first.
Any other question? Students,
Please come forward and ask.
without any hesitation.
Many of the things are new for me as well here. I mean, I've learned over last 3 years. So don't hesitate.
I have a question.
Yes.
Is there any comparisons made for, say, for example, for a mesoscale convective cluster? Any means detailed the dynamics or mass fluxes, various determining aspects. Any verification comparisons made?
For kilometer scale, to my knowledge, not many. I think this paper, so Andreas is working on this. This should be out sometime next year. It's probably one of the first ones. I mean, if not the first, one of the first ones. It's using kilometer scale model data to look into mesoscale convective system. But I might be wrong. I'm not sure.
Considering the global. Okay?
Yes.
Yeah.
Oh, global.
Yeah.
Necessarily. Yeah.
Cam people were working, but what was in my knowledge, they were not good at monsoon.
No, point is mesoscale convective clusters are the kind of rain producing systems. Whether we are able to get them to the accuracy that we require. Very hope. Are there any more questions?
What was the numerical scheme when you are converting Python? Still you are in the spectral or you are going finite difference or finite volume?
Icon doesn't use spectral. So icon is
Finite volume.
Finite volume, finite difference. Some model components use semi-Lagrangian.
Yeah, I can. So you were talking about when you are slowly changing everything into GPT-4
Yeah,
Python.
but we don't change the code. So the functions remain the same.
So you are converting icon
Icon
into
into
Python.
just rewriting icon.
Okay, then,
Not just rewriting.
no,
icon.
rewriting, but the scheme is same. So icon is finite volume that I know. Okay.
Also, it is not coupled, no?
So there is a complete configuration, but we are still trying to make it fast. It is slow somehow.
Was there any? I think it's not in a forecast mode. Was there any test of error growth from let's say 50 kilometer coming to 2.5 kilometer? So what you gain in terms of as a resolution, and then you have a cost of error growth, faster error growth. Is there any assessment how error grows faster in let's say high
And
resolution?
error means
Error means in terms of it is, of course, it is not done in a real forecast mode, but when you go, generally people see that when you go for high resolution, so error your skill spoils very fast. Okay. So in terms of you get very nice horizontal resolution, but when you talk about lead forecast error, that decreases. So you have some trade-off between this. So
this expertise at least is not in the neighborhood in our community. I know one lady Daniela Dominson. She works on it. I had personally approached her, but then she showed interest in looking into heat waves. So if you are interested, I know you do that. That would be wonderful. Yeah.
So, yeah, we'd like to see also the how they are doing.
That is close to me also. I mean, I would personally like to see, yes. Yeah.
Thank you very much.
Yeah, if there are no more questions, I thought there will be more interactions. Okay.
I will have one.
Yeah, please.
Uh,
Anybody getting motivated, please come forward.
Yeah.
Anurag, it was a really nice talk.
thank you.
So, what was of more interest to me, like you told that the transfers of energy from higher scale to lower as well as the vice versa. So there is just some to get that in the exact system means whatever observing system, like I'm going from diurnal to other scale. Suppose some of my errors are there in diurnal. So capture that in other scale, how the error will propagate. So is the computation is the only criteria or somewhere else we can find it out other way around?
Good point. I can only think of computation. So both would know. I can only think of computation, yeah.
So in that perspective, so I need to go for a high resolution model to find it that way.
Yeah.
So it won't be like whichever model I am right now using some 30 kilometer, 40 kilometer grid space. So that won't be able to get me those information.
I know what you mean, yeah. But not to my understanding, no.
We'll discuss later on. Okay, thank you.
Yeah, have you changed any physics components into the model compared with the coarser resolution to the finer resolution?
So depends what is coarse here. So 2.5 kilometers. So as soon as we are at kilometer scale, we turn off convection scheme, gravity wave drag, SSO, subgrid scale orography.
Those are off.
Those are off.
Huh.
For 10 is the gray zone.
Right.
Whereas depending on if one has an interest, for example, the person who was doing.
Or is there something like a scale-aware physics which is working inside the model, which can take care of the resolution and the processes?
Yeah, I know. I mean, I know what you mean.
Mm.
Well, I personally don't believe in scale-aware physics. Nothing comes for free.
Mm.
But there is one, which, so the turbulence scheme in ICON, if I'm not mistaken, I only recently discovered that it has some kind of scale awareness.
Okay.
At some point, we will remove it.
Okay.
It's because this is my personal choice, but it is. But normally, no, we don't have scale-aware physics, I think, to my understanding.
And another is just like a simple thing, how you validate this model at higher resolution. Because finally, when you are comparing with the coarser resolution, you are bringing both the models to the coarser resolution and comparing the performance. So you are losing the advantage of higher resolution. So somewhere, is it compared with the higher resolution validation? And another thing is the data going in may not be at such a higher resolution. So how you, in the assimilation process?
I'll first add that all these are targeting for people interested in climate studies.
Yeah.
So there's no assimilation involved. You just let it run for free.
Okay.
Unless there is a specific user who has an interest.
So I understand that. And for verification in the validation way?
So when we validate, we do it differently. I totally understand what you're saying. For some things, we bring them to the same resolution.
Yeah.
For some things, we don't. We compare them on the native grid at the same time. So all these simulations have happened since January. So there are only 2 papers which are coming out. One on Jetstream, where she looked into, as I said, same grid, at the same time, native grid. And the second paper looking into global monsoon system that Praveen has been working on. So we haven't published many papers yet. We really, expertise. Again, I mean, people have to have expertise to look into it.
Interesting, but work is very interesting.
Thank you.
So thank you all for the nice interactions, and let us now thank Dr. Anurag.
Yes, all the time.